Number one, a ball of mass 2.7 grams is released from rest from a height of 28 meters above horizontal ground. This is the diagram. This is the position of the ball, and the height is 28 meters from the ground. So that in the absence of air resistance, the ball impacts the ground with a speed of about 23 meters per second. Right. In this phenomenon, ball has two energy that the first is potential energy. The potential energy it has, uh, the equation is m times g times h. And then when this ball hit the ground, when it hits the ground, it has kinetic energy from this position to the ground, and the kinetic energy formula is half m v squared. M is mass. It's 2.7 grams. Mass, I would like to convert into kilogram. 2.7 times 10 power minus 3 kilogram. And it has height 28 h and gravitational force 9.81. Right. So it means uh, show that the absence of a resistance, the ball impacts the ground with a speed of about 23 meters per second. So I'm going to using a formula. Uh, this formula this formula is by the conservation of mechanical energy, that potential energy equal kinetic energy. Okay. This equation based on conservations of mechanical energy. P this one and KE this one, kinetic energy and potential energy. So M times G times H equal half times M times V squared. We are going to prove that speed is about 23 meters per second. Speed, it means we have to find V. So V equal square root of 2 times M G H over M. V equals square root. M is this one, 2.7 times 10 power minus 3. Okay. Times 2 times G, 9.81 times H, it is 28 meters over, okay, over, it is with 2 times, yeah, over M, right? M is 2.7 times 10 power minus 3. Yeah, the square root. And if you calculate, the result is square root of 548.89. Phi equal 23.42. We have to convert becomes significant figures. 23.4. Or according to this request is 23 meter per second. Another resistance force acts on the ball. F can be modeled by this equation F equal kv squared, where v is the speed and k is a constant. Determine the unit of k in terms of fundamental units. Right. The force is measured in Newton. Okay. Force is measured in Newton. Uh, and after that 1 Newton, I would like to write it here, better here. 1 Newton actually equal 1 kilogram meter per second square. This is 1 Newton. Kilogram is the unit of mass, and m is the unit of length or a meter, as a unit of time or second. So the unit of force is this one. This is the unit of force, the unit of F or force. Next, the unit of velocity. Now, the unit of velocity or speed, units of velocity or speed is v is meter per second. It means if v squared, it is meter per second squared, or v squared equal m squared s power minus 2. Right. So the equations for force, according to this information, that F equal k v squared. If k is the subject, this formula becomes F over v squared. F unit is this one, kilogram meter per second squared, while v squared unit is this one, squared s minus 2, s power minus 2. Divided equals 1, and it becomes kilogram over meter, or kilograms meter power minus 1. And this is the fundamental units of K, the unit of K, based on the fundamental units. Describe how the ball reaches the terminal speed. This is my explanation. I have provided this. The ball reaches terminal speed when the upward force due to the air resistance becomes equal to the downward gravitational force. At this point, the ball stops accelerating and continues to fall at a constant speed. The speed is known as the terminal velocity and is determined by the mass of the ball, the air resistance constant, and the gravitational acceleration. You may add your sentences, your words, or your opinion. The graph shows the variation with time t of the speed v of the ball from the instant it is released until it impacts the ground. So if you look this graph, the vertically axis is the axis of velocity with unit meter per second. The horizontally axis is the axis for time with unit second. Question: state the value of the area under the curve. The area under the curve is the displacement. How we determine the displacement? based on this curve, this graph. Look that this graph will be constant. This line will be the strike line starting on t equals 3. When t equals 3, it means phi equal, this is around 9.5. This is 9.5. 9.5. Okay, so displacement equal 9.5 times 3 equal 28.9 meters. Or you may round it, becomes 29 meters. Determine K. We're going to determine K. At terminal velocity, uh, the force the force in air equal force of gravitational force. This is the conditions when terminal velocity. So it means F F air is K times V squared based on the previous information, and Fg equal M times G. Based on this equation, we can determine K. K equal M times G over V squared. So it means K equal M is 2.7 times 10 power minus 3. G is 9.81 gravitational force. And phi is 9.5 squared. Why 9.5 squared? Because through graph, we can determine 9.5. The terminal velocity occur on 9.5. This one, 9.5 occur here, the velocity. The terminal velocity occur on velocity 9.5. So that's why this is 9.5. Okay. If you calculate K equal 0.2934 times 10 power minus 3, or K equal 2.9 times 10 power minus 3. That is K. On the axis below, draw a graph to show the variation of the magnitude of the resultant force. On the bar with time t, no numbers are required on the axis. There's no number, we just create our graph, right? But I will explain about three things regarding we are going to sketch this graph. The first, that graph starts at the high volume, corresponding to uh, the gravitational force. It means at the at the at the high around here, for example, around here, okay, and then two downwards. So the graph decrease. It decreased over time reflecting to the increased air resistance. It's the graph towards downwards because the increasing of air resistance. Air resistance increase and the graph will be decreased. Okay, the force will be decreased. And the third is the graph will be flatter out. It will be flatter out at zero. This, wait, flatter out at zero. Okay. That's indicated that the resultant force is zero when terminal velocity is reached. When terminal velocity reaches, the resultant will be zero, like that. Calculate the average power dissipated by the air resistance force. The energy dissipated by air resistance has expressions E. E dissipated or energy dissipated equal potential energy mgh minus kinetic energy half m v squared or m times g h minus v squared minus half v squared. So we can find the value of energy dissipated. M is 2.7 times 10 power minus 3. G is 9.8, 9.81 times H is 28. Okay. And then half. Okay, velocity is 9.5. And if you calculate, the result will be 0.620 joule. Now, we are going to find, after that, we're going to find average power. Average power, which unit is what? According to the graph that uh, energy dissipated occur in T equal 3.6. Okay. As you can look here, the graph. Okay. It stopped at this point, 3.6, this one, 3.6. And now I'm going to determine average power. Average power equal energy dissipated over time. 0.620 over 3.6 second. This is joule. It is 0.17 Newton. The ball rebounds from the ground with speed 7.8 meter per second. The ball is in contact with the ground for a time t. The average resultant force on the ball during this time is 1.1 Newton. Okay, the average resultant for the average force is 1.1 Newton. Determine T. The change in momentum formula expression is delta P equal m times Vp Vi. Okay. Before and after. So delta P equal m is 2.7 times 10 power minus 3. and this is 7.8. This one with the speed, and then minus 9.5 or 9.5. You can why we determine 9.5 from the graph. Okay. Okay, so it's gonna be if calculate it comes 0.0467 Newton second. According to the impulse momentum theorem, that according to impulse momentum theorem, that force force average force average equal delta P over T. For average is this one, 1.1. Ergo, if T is the subject, it means this formula becomes delta P over F average. So it's going to be delta P this one, 0.0467 Newton second over this one, force average 1.1 Newton. And the result is 0.042 seconds. Number two, cruise ice of mass 35 grams at temperature minus 10 degrees Celsius is placed in a warm room. The graph shows the variations of the temperature T of the ice with time T. This is the graph. The specific heat capacity of ice is 2100 joule per kilograms per Kelvin. Show that the average rate at which thermal energy is being transferred into the ice is about 3 watts. The formula for determine thermal energy is Q equal M times C times delta T. But I would like to identify MC delta T. M is mass of the ice is 35 grams. 35 grams convert to kilograms becomes 0.035 kg. C is this one, the specific heat capacity of ice. This is the number. And delta T, we have to convert from Celsius to Kelvin because the specific heat capacity, uh, the this is on Kelvin, not on Celsius. Okay. The temperature. Uh, no, zero degrees Celsius equal 273, 273.15. Yeah, 273.15 Kelvin. While minus 10 degrees Celsius, it is equivalent with 263.15 Kelvin. I have checked this one. So the temperature, if you look on this graph, 0 to minus 10. So it means 0 minus 10 in Celsius. But if we convert in Kelvin, it becomes 273.15 minus 263.15, and it is 10 Kelvin. Okay, so the temperature 10 Kelvin. Now we're going to substitute this information into this formula. Q equal M is 0.03 kg times this one, 2100 joule over kg over K, delta T 10 K. So K. Now I have calculated this and the result is 735 joule. Now we are going to uh, determine, we will figure out the average rate, yeah, average rate of power. So it means power, or yeah, the average of power. The formula is Q over delta T, 735 joule over 4 times. I'm going to show you on this graph. From minus 10 to 0, look, there are one, two, three, four. Okay, four. Okay, four. Minutes, it means 4 times 60. 60 per second. This. So the result is, I have calculated this, 3.0625 watts. In a significant figures, 3.1, 3.1 to 0.6 watts. Estimate the specific latent heat of fusion of ice. That, right. The total thermal energy required to melt is, the formula is Q. I would like to Q melt. Q melt. Well, the name is Q melt is power times T. Time T when melting. P is this one, but I would like to using this number 3.0625 times, there are 60, if you look on graph, there are 60 minutes times 60, convert into second. And so it's going to be, if you calculate the result, wait, I will calculate on my calculator. 11,025, or it is 1.10 times 10 power 1, 2, 3, 4. Okay, joule. Now, specific latent heat of fusion, the formula is L. Okay, the symbol is L. L fusion. I would like to L fusion equal Q melting over M. This is the formula. Q melting is 1.10 times 10 power 4 joule over M is just now 0. Let me see the mass. I forgot mass. This one. 0.035 kg. And I will calculate, wait on my calculator. 1.1 times this one. 3.1 Yeah, times 10 power 5, 3.1 times 10 power 5 joule kg power minus 1. Next, between 4 minutes and 64 minutes, solid ice and liquid water coexist at 0 degrees Celsius. Compare and contrast. During this time, the internal energy of solid ice to that of an equal mass of liquid water. I have provided my opinion, my explanation about it. The thermal, the internal energy of liquid water at 0 degrees Celsius is greater than the internal energy of solid ice at 0 degrees Celsius due to the greater kinetic energy of the molecules in the liquid phase, more freedom of movement, and also the lower potential energy in the liquid phase due to weaker hydrogen bonding compared to the solid phase. This is my opinion. You may add with your words or with your sentence. Number three, outline what is meant by a traveling wave. I have provided my explanation about this. A traveling wave is indeed the transfer propagations of energy, momentum, and information through a medium or space. The loudspeaker emits sound of frequency 210 Hertz into a pipe with one open and one closed end. Okay. The diagram shows a representations of the standing wave established in the pipe. So the length of the pipe is 1.20 meters. Outline how the standing wave is formed in the pipe. Right. Before I continue, okay, I will show you my explanation about this question first. The standing wave is formed due to the interference of the incident and reflected sound waves with the closed end of the pipe creating a node and open end creating an antinode. The length of the pipe determines the wavelength of the standing wave and the fundamental frequency, 210 Hz. It matches the conditions for this wave to form in the pipe. Next, determine the wavelength of the wave, right? The first I will I will explain about this wave. Okay, this is actually not one wave because the wave only this from this point to this point. This is half wave. And from this point to this point, or from this point to this point, that is 1/4. Okay, a quarter. So half plus a quarter is 2/4 plus 1/4, 3/4. Okay, 3/4 wave. So determine the wavelength of the wave. Lambda, the formula is lambda equal L over uh, L over 4, yeah, 3/4 because the wave is that one is 3/4 wave according to my calculation list. So it's gonna be 4L over 3. L is 120, 4 times 120 over 3. And the result is 1.60 meters. Calculate the speed of sound in the pipe, setting the answer to an appropriate number of significant figures. Right, I'm going to using this formula that velocity or speed equal frequency times lambda. Okay, frequency is 210 and lambda as we calculate 1.60. And if you calculate, the result is 336 meter per second. The solid line represents the standing wave at time t, and the dot line represents the standing wave at an instant later. This is the dot p. The dot is the equilibrium positions of a particle p in the pipe. Equilibrium position. The up arrow indicates the displacement to the right, and the down arrow displacement to the left. Okay. On the diagram, draw a dot to indicate the approximate positions of P at time t. Okay, so we need to find the equilibrium position. When the dot on equilibrium position, when the dot on equilibrium position here at the midline, this is the equilibrium position. Okay, so the dot position, uh, position of P at time t, P is this dot positions at according to equilibrium position. An arrow and as well draw an arrow to indicate the velocity of P at time t. The velocity direction to the left, the direction to the left. E. The amplitude of oscillations of standing wave in part B is 4.2 millimeters. The mass of particle P in part C is 1.8 times 10 power minus 6 kg. Calculate the total energy of P. We need to find the angular frequency first, angular frequency omega. Okay, omega formula is 2 pi times f, frequency. So 2 pi times frequency is 210. And the result is 1.319 times 10 power minus power 3, 10 cube radian per second. That is omega. Energy of a particle in sample harmonic motion, I will use the formula. The formula of energy of particle in sample harmonic motion is, wait, yeah, this one. E equal half times m times omega squared times displacement. Okay. Sorry, amplitude, not displacement. This is amplitude. Okay, amplitude is one 4.2 millimeters, but I'd like to convert into meters. So 4.2 times 10 power minus 3 meters. Okay, and then it means energy equal half times mass is 1.8 according to this information. 10 power minus 6 kg times omega is this one, 1.319 10 cube times amplitude. Amplitude is 4.2, 10 minus 3, 10 power minus 3. I have calculated this, 2.8 times 10 power minus 5 joule. This the result. Okay, after approximation becomes 2.8. The displacements of P, we are going to calculate the displacements of P when its kinetic energy is equal to its potential energy. At the point when kinetic energy equal potential energy, we can set that uh, kinetic energy half m times omega squared times displacement squared is equal half of m times omega squared times amplitude squared. You recalculate this part on the previous question. So if d is if because we are going to find displacement, if d the subject is gonna be half divided by half equal 1. So it's gonna be square root of this one half m omega squared a squared over m omega squared equal 1 is the root half a squared. So d equal square root half times a. So half times square root half times a is 4.2 in millimeters. So the result is 2.9698 rounded to 3.0 millimeters. Or if in meters becomes 3.0 times 10 power minus 3 meters. The frequency of sound is reduced to 140 Hz. Explain why. A standing wave will not be formed in pipe. I have provided my opinion about this. The frequency of 140 Hz is not an odd multiple of the fundamental frequency, 70 Hz. So the pipe cannot support a standing wave at this frequency. Standing waves only form at odd harmonics of the fundamental frequency. Odd harmonics are 70 Hz, 210 Hz, 350 Hz, so on. Therefore, a standing wave will not be formed at 140 Hz. Number 4, the diagram shows a junction in a circuit. The circuit, this with junction. The currents in the three wires are related I1 equal I2 plus I3 given in this circuit. State the fundamental law of physics from which the relations is derived. Okay, so I have provided my answer, my explanation. This one. The relations of I1, this, equal I2 plus I3 at junction, wait, at the junction, I have to Okay. The relations of I1 equal I2 plus I3 at the junctions in the circuit, is the junction, is derived from the conservations of electric charge and is formalized through Kirchhoff's current law. Okay, I think clear. B. A cell of electromotive force 1.50 volt and internal resistance R, so R is the internal resistance, is connected to a resistor of resistance 5 ohms and ideal voltmeter V. This is the circuit. The reading of the voltmeter is 1.2 volts. Determine the internal resistance R of the cell. Okay. So to determine the internal resistance, we can use the formula derived from the relationship of EMF, electromotive force, and the terminal voltage and the circuit. And the formula is V term. I'd like to using V term. V term, it means V terminal velocity equal EMF epsilon minus I times R, current times internal resistor, okay, which EMF is 1.5 volts, 1.50, and then R or external, this is external resistor, R is 5.00 ohms, and V terminal velocity 1.2 volts. Okay. As well, the current in the circuit, can be found using using Ohm's law for the total circuit. Ohm's law and for the total circuit says that I equal EMF over external resistor plus internal resistor. Now substitute this equation into this equation. So V terminal velocity equal epsilon minus epsilon over R plus R times R. Or I would like to continue here that V terminal velocity equal epsilon times epsilon minus R over R plus R times epsilon, like that. And I would like to factorize and divide, becomes V terminal velocity over epsilon equal 1 minus R over R plus R. Or it's gonna be, if one move here, becomes minus V term over epsilon plus 1 equal R over R plus R. And it means minus V term, minus V terms, 1 is epsilon over epsilon, V term plus epsilon over epsilon, R over R plus R. And after that, substitute this information, substitute this number into this equation, becomes minus 1.5, sorry, minus 1.2 if you term this one, minus 1.2 plus 1.5 over epsilon is 1.5 equal r over uh, 5 plus r. This is 0.3 over 1.5 equal r over 5 plus r. So it means this is 0.3 over 1.5 is 1 over 5 r over 5 plus r. Now multiply this. If multiply, it becomes 1 plus 1 over 5 r equal r, or r minus 1 over 5 r equal 1. 5 minus 1, 4 equal 1. So r equal 1 times 5 over 4. It is 1.25, and the unit is ohm. A second 5 ohms resistor is connected in parallel to the first resistor, the circuit. When a second ohms resistor connected in this circuit. State and explain the change, if any, in the voltmeter reading without further calculation. Without calculation, we are going to explain. I have prepared my explanation this. When the second 5 ohms resistor connected in parallel to the first 5 ohms resistor, the voltmeter reading will decrease slightly. This is because the total resistance in the circuit decreases, leading to an increase in current. So potential difference across R increases. I'm going to add my explanation, my my explanations uh, my about this explanation that for 2 ohms resistor in parallel, you know that the R total or resistance total of two 5 ohms equal 5 times 5 ohms times 5 ohms over 5 plus 5 ohms. And the result is 25 over 10. This. And it is 2.5 ohms. 2.5 ohms, 2.5 ohms is, if you compare with uh, with with those resistor 5 ohms, this is lower, 2.5 lower than the resistor. Okay, the first resistor and the second resistor. The this resistor are 5 ohms, while this one only are total only 2.5 ohms. So the effect on current, the implication on current, first the implication on current formula is epsilon over uh, R total. Okay, if R total 2.5 lower than 5, the implications I or current will be increased. That's for current. The implication for voltage. The voltage formula is epsilon minus I times R. If I increase the implication, the terminal voltage, this if I increase the terminal voltage will be decreased. Okay. If I increase, because this number will be increased as well. And the implication for potential difference across R, the potential difference across R, uh, the 5 ohms resistor will be the potential difference will be decreased. I mean the potential difference across R. Potential difference across R would be decreased. I think this is clear. C. Proton moves on a circular path in a region of uniform magnetic field of magnetic flux density B that is directed into the plane of the page. It is the proton with the circular path as a circle. On the diagram, draw an arrow to indicate the velocity of the proton at the position shown. This one. Okay. The magnetic force in proton that is always perpendicular to the velocity of this proton. And the velocity is the tangential of the circle for every point. So it means uh, the arrow, okay, the arrow is to downwards perpendicular and okay like this. The direction to downward. Next, show that the frequency of revolution of the proton is given by F equal EB over 2 pi MP, right? I will explain about this. The magnetic force, I would like to use in this area first. The magnetic force, or FB, on the proton. So FB is the magnetic force. This magnetic force on this proton, I need to using this diagram, proton, because of the magnetic field, we can express as FB. If FB is a symbol of magnetic force, that FB equal E times V times B. E is the proton charge. V is the velocity of this proton. Okay, while B is this magnetic flux. Okay, and the flux magnetic. Okay, and then the centripetal force F. Okay, the centripetal force required to keep the proton moving on this circular path. It has radius. With the radius, if this is the center of this circle, if the radius, we can express that F, that centripetal force equal mp. This is mass of proton times v squared. This is the velocity of proton over r. R is the radius of this path, the circular path of proton. So next, when the magnetic provides the centripetal force, we can combine between this F dash force becomes F equals F, F equals F, F equals F. Here, FB equals F. Or magnetic force equal uh, the centripetal force. It means we are going to writing E V B times E V B equal MP times V squared over R. We are going to determine F. So it means to determine F, we need to find R or radius. So if radius is the subject, this formula we can rearrange becomes MP times V squared over E times V times B. Divide and becomes MP times V over E times B. Yeah, that is the radius. Next, the proton moves on a circle. When this proton moves on the circle, it means the distance from the initial point until it returns to the initial point, that is one circumference, circumference. And one circumference formula is 2 times pi times r. Okay, so wait. One circumference, if we calculate the time taken to complete one circumference, wait, I still need this information. If we would like to calculate time taken for one circumference, we can use the formula that T equal one circumference over velocity. This is the formula to calculate time taken for one circumference. Next, one circumference formula is 2 pi times r. So it means 2 pi times r over velocity, right? So it means we can substitute this into wait, yeah, substitute not this r into this formula. I would like to writing here. So equal 2 pi r over v. We're going to substitute this fraction into this r. It's going to be mp v over e b over v. So it becomes mp v over eb times 1 over v. Divide. Okay, so it's going to be mp over e times b. Right. To find frequency or f equal 1 over t. Okay, so it becomes 1 over this fraction MP over EB, or uh, EP over MP. So prove that F equal EB over over MP. I forgot that is 2 pi, supposed to be 2 pi here. Wait, pi here. I forgot to add 2 pi. This is 2 pi. This is 2 pi as well. This is 2 pi. It means 2 pi here. Wait, I'm gonna fix it. So EB over 2 pi MP. Okay. This is frequency, same like this one. Okay, next. The magnitude of B is 2.5 Tesla. Calculate the frequency of revolutions of the proton. Right, so I will using this formula that frequency equal EB over 2 pi MP. uh, E is E is charge of proton, and charge of proton is 1.6 times 10 power minus 19. Okay. And then B is this one, 2.5 Tesla. And then MP is mass of proton. Mass of proton is 1.67 times 10 power minus 27. Right. And F, it means we are going to substitute this number, becomes 1.6 times 10 power minus 19, 2.5 over 1.67 times 10 power minus 27. And if you calculate, the result is 3.81 times 10 power 7. The unit is hertz. Number 5, a probe of mass M has landed on the equator of a rotating asteroid of mass M and radius R. This is a diagram. This is the probe. The asteroid rotates with angular speed omega. By drawing a free body diagram for the probe, show that the normal force N is normal force on the probe from the asteroid is given by N equal this expression, M times Gm over R squared minus omega squared times R. Right. The probe is subject to the gravitational attraction of the asteroid, which is given by formula F. Wait, I'm gonna writing here. It's just given by a formula. I'm gonna writing here. F equal Gm times M over R squared. Okay. So the directions of this force is to the left. Okay, that. And then, yeah, this is the formula F, the force or the force of gravitational force. G is the gravity constant. M is the mass of asteroid. This M is mass of probe. And then R for radius of asteroid. And the centrifugal force is given, centrifugal force. The centrifugal force given by the formula m times omega squared times r. Omega is the angular speed of the asteroid. Right. The normal force must balance with the sum of it. I will scroll down. Must balance with the sum of the gravitational force and centrifugal force. So centrifugal force uh, and then the gravitational force must be balanced. So we can have the equations about the normal force balanced with the sum of gravitational force and centrifugal force like this. I'm going to write it here. The normal force equal gravitational force minus F centrifugal force. Right. So F gravitational force is this one. So N will equal this expression, this fraction over R squared minus the centrifugal, this one, M omega squared times R. Or we can factorize, it becomes M times G, M over R squared minus omega squared times R. And that's what next we move to part B. Deduce that the probe will remain on the asteroid surface only if omega less than or equal square root gm over r cubed. Right. According to part A, that n equal, wait, I'm gonna write it here, n equal m times gm over r squared minus omega squared times r. When then when normal force equals when normal force when n greater than or equal 0, so this equation becomes gm over r squared minus omega squared r. It is greater than or equal 0. That this m divided by 0 equal 0. Or wait, this is not r2, this is r squared. Okay. Or we can writing that omega squared r is less than or equal this one, this expression gm over r squared. And r divided by r, it becomes omega squared. Oh, sorry, times r times r squared becomes gm over r cubed, or omega equals square root gm over r cubed. Same with this one. sorry, less than or equal, less than or equal. Okay. Another probe orbits the sun. The distance between the probe and the sun is 4 times the distance between the Earth and the sun. Show that the intensity of the solar radiations at the surface of the probe is 85 watt per meter square. Right. So the formula I'm going to use is intensity of probe equal intensity of Earth. Okay, this is intensity of Earth. It equals P intensity of probe is P over 4 pi times 4D squared. Okay, over P over 4 pi times D squared. So this part is the numerator is intensity of probe and the denominator is intensity of Earth. Okay, right. And it equals 1 over 16. 1 over 16. Why 1 over 16? Because 4, 4 squared is 1 over 16. That's 1 over 4 squared. And we can continue with the simplifications. P over 4 pi over d squared, 4 pi d squared, P equal 1, equal 1, as well d squared. Okay, so this is 1 over 16 proof. So 1 over 4 squared, that is 1 over 16. So it means intensity of probe over intensity of Earth equal 1 over 16. Right. The next, intensity of probe over intensity of Earth is 1360. Okay. Over 1 over 16. And intensity probe equal 1 over 16 times 1360. And the result is, wait, 85. 85.0 watt per meter squared. Estimate the equilibrium temperature of the probe, assuming it behaves as a block body. So equilibrium temperature symbol is T. So we are going to figure out T, right? Now I'm going to using this formula that sigma times T power 4 it equals intensity. Intensity is this one, 85. Sigma is Stefan Boltzmann constant, 5.7 Boltzmann constant, 5.67 times 10 power minus 8 watt meter power minus 2 um, K power minus 4. This is Kelvin. And then Let me continue with these calculations. If we are going to find T, it means T equal I over sigma power 1 over 4. It means it is I is 85 over this number 5.67 times 10 power minus 8 power 1 over 4. And if you calculate this, you will gain the number. The result is 196.7, rounded to 200. And in significant figures, it is 2 times 10 squared. The unit is Kelvin's temperature. Number 6, wait. Quarks are elementary particles. State what is meant by an elementary particle. I have provided my explanation about this. An elementary particle is a fundamental particle that is not made up of smaller constituents or subparticles, but it is considered a basic building block of matter. It means it cannot be divided or broken down into simpler particles. I think it is clear for you. Next, list the fundamental forces that act on quarks. This is my answer. There are 4: electromagnetic force, gravitational force, strong force, and weak force. Now this one. The lambda baryon has quark content UDS. U is up quark, so lambda baryon contains of one up quark, one down quark, and one strange quark. So lambda baryon decays according to this reaction. Lambda baryon being this is proton and pion. The quark content of pion is antiquark and down quark. So that is pion. State and explain which fundamental interaction is responsible for this decay. Right. So if you look this reaction, this is, I will say this is the initial state and this is the final state. So initial state, this is from the lambda baryon, while the final state consists of proton and pion. So pion consists of antiquark and down quark. If we compare the initial state and the final state, that I would like to write in here that one of the string quarks, one of the string quarks or the symbol S, this is this one of the string quarks in lambda baryon, the symbol is this one. It's transformed into up quark. It's transformed into up quark. So from baryon, the strange quark from baryon transform into up quark, right? And into here the final state. The second, this process produce produce a boson, W power minus, this is boson, which decay. Now, better I will add. I'm gonna add subsequently decay, which subsequently subsequently decay. Sorry, should be this decay. We subsequently decay into into down quark and anti-quark. So this is one down quark and one anti-quark. This one, okay, on this one, on pion. So my summary, my conclusions from this information that this reaction, this reaction this reaction is mediated by the weak interaction. Because it involves it involves it involves a hallmark of the weak force. So the weak force implicated that this reaction actually is the weak interaction, mediated by the weak interaction. Okay, I have explained about the weak interaction and the weak force. Right. This one B. By reference to the concept of binding energy, explain why the combined mass of the nucleons of a nucleus is greater than the mass of a nucleus. I have provided also my explanation about this. Binding energy is the binding energy. Wait, binding energy is the energy that holds the nucleons together within the nucleus. The energy required to break the nucleus into its individual protons and neutrons. Okay, and the second, my information that according to Einstein mass energy equivalence principle, this formula energy equal m times c squared, that energy and mass are interchangeable. This means that the binding energy of the nucleus also has a corresponding mass. The third, the mass defect is the difference between the mass of the individual nucleons when it free. And the mass of the nucleus. Okay. So when okay, okay, when nucleons come together to form a nucleus, they release energy in the form of binding energy. This release of energy results in a decrease in mass. And the fourth, the mass of the nucleus is less than the sum of the individual masses of the protons and the neutrons because some of the mass has been converted into binding energy. And based on this information, this four informations, my summary, so the binding energy reduced the total mass of the nucleus compared to the sum of the masses of the individual nucleons. So that's why uh, the combined mass of the nucleons is greater than the mass of the nucleus itself. I think that is clear. That's completely information to you. Next, the following binding energies per nucleon are available: thorium, radium, and helium. So determine the energy release in the decay. Right. So energy release we gain through multiply and then uh, minus between the energy release and between the initial energy and the final energy, or this part is the binding energy product, and this term is the energy release. So energy release minus the binding energy product, that is Q. So total energy release is uh, this term minus this term, the energy release minus the binding energy product. So energy release is um, 224 times this one, radium, 7.67 9917 plus helium times 1, 4 times 7.073915 minus the binding energy product, 228, that's one. 7.645074. And the result is 5.520. Okay. The microelectron volt. I think clear. That's one. It is observed that sometimes the alpha decay of thorium is accompanied by gamma ray emission, suggests an explanation for these observations. I have provided also my explanation about this. The alpha decay of thorium is accompanied by gamma ray emissions. If you look uh, this reaction, okay, based on we are going to explain based on this reaction. I have provided also my explanation about this, that when thorium undergoes alpha decay, when thorium, okay, I'm gonna writing here when this the reaction proton, proton plus ion. This one. So the binding energy is thorium becomes radium and helium. So when thorium undergoes alpha decay, it emits an alpha particle and transforms into a different element. However, the new form nucleus is often left in an excited state after the decay process. The second, my information that to reach a more stable, lower energy state, the excited nucleus can release excess energy in the form of gamma rays. Gamma rays are high energy photons that are emitted as the nucleus transitions from an excited state to its ground state. This emissions of gamma rays is a common way for the nucleus to shed the extra energy gained during the decay process. So based on this information, my summary, the observation that alpha decay of thorium is sometimes accompanied by gamma ray emission can be explained by the fact that the daughter nucleus often ends up in an excited state and releases gamma rays to reach a more stable energy level. We have discussed about this theory, also this problem when I explained on our classroom. So students, you can evaluate uh, your lessons when we discuss about this lesson. All right, let's continue. Number 7, light of wavelength lambda diffracts at a single rectangular slit of opening B. The diagram shows two rays of light leaving the top and the middle of the slit. The rays come from the same wavefront. The angle of diffraction is theta. For small angles, the approximation sin theta equivalent with theta may be used on this diagram. Uh, this is the slit, right? Next. The rays, these are two rays. This is the first rays and this is the second rays. The rays meet at point P on a screen, a very large distance from the slit. Okay. Show that the phase difference between the two rays at P, at point P, two rays at point P when they meet at point P, the phase difference is pi b theta over lambda. Okay. For identifications, the first that is according to this information, we have several information that lambda is the wavelength, and then B is, I'm going to writing here, B is the slit width, this width, okay, and the slit of this this slit. Next, while theta is the angle of diffraction, and then so theta angle of diffraction because these are two rays. This is the first rays and this is the second rays. While the next information, the third information, one, two, three, the fourth is this is that diffraction theta. This is the angle of diffraction. Theta is the angle of diffraction. And then the fourth information that sine theta equivalent with theta. Now, the question is about show that the phase difference between the two rays at P is this one, pi d theta over lambda for diffraction at a single slit. Wait, I'm going to for diffractions at a single slit, the phase difference between the two rays, the first ray and the second rays, between the two rays at point P is due to the path difference between them. So because of the light rays are leaving from the top and the middle of the top and the middle of the slit, this is the slit. The distance between 2 points, between this point and this point is b half. So this is b half and this is b half, the distance, right? B half, also b half. Next, for small angles, the path difference I would like to write. This is the path difference. Path difference. Okay. For small angles, the path difference between the rays, between the first rays and the second rays, we can approximate it using trigonometry. That delta x, okay, sorry, delta x is the path difference because difference between path difference and phase difference. This is phase difference, right? So we are going to using a trigonometric rule that delta x equal b half sine theta. According to this information that sine theta equivalent with theta, so we can simplify delta x becomes b half times theta, or delta x equal b theta over 2. The phase difference, this is the phase difference. The phase difference is related to the path difference, pH related to delta x by this rule that phase difference equal to pi over lambda times delta x. This is the relationship between the phase difference and the path difference. So if we substitute delta x equal b times theta over 2, so phase difference will be 2 pi over lambda times b half times theta. Becomes 1, divide. So it's going to be pi b theta over lambda. So the phase difference pi b theta over lambda. The two rays interference destructively at P to form the first minimum of the single slit diffraction pattern. Explain why theta equal lambda over B. Okay. When two rays interfere destructively, it means it means the two rays are cut off phase by half of wavelength. Okay, half of wavelength is it means it's one, but half of wavelength is it's one or half wavelength, half lambda. For a single slit diffraction, the condition for destructive interference at the first minimum, it's happening when destructive interference at the first minimum is when the path difference between two rays is equal to one of wavelength. Again, it's happening when the path difference between two rays is equal to one wavelength. One wavelength is one lambda. We have Now we have the path difference that delta x b sine theta. That is the path difference. For small angles, according to the previous information for small angles, that sine theta equivalent with theta. So it means delta x, I would like to writing here delta x equal b, according to this information, that b times theta. Next, for the first minimum, the path difference delta x, the path difference delta x is supposed to be equal lambda. So delta x is supposed to be equal lambda. So it means if delta x equal lambda, it means b times theta equal lambda, because delta x equal b times theta. That is for the first minimum. So if we simplify, theta becomes the subject of this equation. So theta equal b over lambda. We can rearrange like this, this equation. Next, the James Webb Space Telescope GWST has an effective diameter of 6.5 meters. Calculate the smallest linear size at a distance of 13.6 billion light years. It is 1.3 times 10 power 26 meters. It equivalent with 13.6 billion. 13.6 billion in we can convert into 1.3 times 10 power 26 meters. This is insignificant figures that can be resolved by the GWST when it operates at a wavelength of 1200 nanometer. We need to use the formula for angular resolution. The formula for angular resolution, given the diffraction limit that theta equal 1.22 times lambda over d. Lambda is the wavelength of light, and then d is diameter of the telescope. Okay, James Webb Space Telescope. James Webb Space Telescope diameter is one, and the diameter of James Webb Telescope is, according to this information, that this one 6.5. Right. Now we are going to calculate that theta equal 1.22 times lambda is wavelength. One. Okay, the wavelength of light. This one point uh, 1,200, but 1,200 nanometer. In significant figures, this is 1.2 times 10 power minus 6 meters, so 1.2 times 10 power minus 6 nanometer over 6.5, according to this information. So if you calculate, the result is 2.25 2.25 times 10 power minus 7 radians. So now we will convert, I will convert 13.6. I'm going to convert this one, 13.6 to 2 meters. And then, so the distance is, the distance 13.6. Better using this one, 1.6. 1.3, I mean, not 1.6, 1.3 times 10 power minus power 26, okay, times 9.461 times 10 power 15, okay, meter per light years. So it's going to be 1.287 times 10 power 26 meters. Okay. So this is the distance. And then now the smallest linear size is theta times distance. Okay. Theta is 2.25 times 10 power minus 7 radians times this one 1.287 times 10 power 26 meters, and the result is 2.9 times 10 power 19 meters. I have explained this on our previous lesson, so students, can you can evaluate your notebook. Okay, right. Next, the GWST can also operate at wavelengths longer than 1,200 nanometers, suggests whether the resolution of the telescope is improved at the longer wavelength. I have provided my my opinion about this question, that for the James Webb Space Telescope GWST, the resolution is influenced by the wavelength at which it operates. The formula for angular resolutions are 1.22 it informs us that the resolutions, this is theta actually, this is theta, resolution theta is directly proportional to the wavelength. It means the wavelength is lambda. The wavelength increase, the implication that the angular resolution, also this is theta, is also increased. Okay, so if the wavelength increase, The implication, the angular resolution as well increase. An increase in angular resolution corresponds to a decrease in telescope's ability to resolve finer details or longer wavelengths result in poorer resolution. Therefore, when the JWST operates at wavelength longer than 1,200 nanometers, the resolution of the telescope is not improved. So, not improved. Instead, it is diminished. The telescope will be able to resolve larger structures, but will not be as capable of distinguishing finer details compared to when it operates at shorter wavelengths. I think it is clear for you students. A uniform spherical planet P has mass m and radius r. A projectile of mass m is launched with kinetic energy to gm m over 3r from the surface of P. Determine whether the projectile will escape the gravitational field of P. Let's start by comparing the kinetic energy of the projectile with the energy required to escape. Right. The escape velocity, is given by this formula that the escape velocity uh, is square root to gm over r, which g is gravitational constant, m is mass of the planet, r is radius of planet. The kinetic energy needed to achieve this escape velocity through this formula, kinetic energy escape. Okay, the kinetic energy to escape equal half mv squared. This is the formula of kinetic energy. Yeah, of course, this is v escape, right? If we substitute this uh, equation into this formula, it's gonna be half m times square root 2gm over r squared comes half m 2gm over r. Okay, it equal gm m over r. Okay. Now we can compare this kinetic energy escape with the kinetic energy when projectile launch. Kinetic energy when projectile launch. This one. Okay, kinetic energy when projectile launch is 2 times gmm over 3r. If we compare between this kinetic energy and this kinetic energy, that this kinetic energy escape is is greater than this kinetic energy when the projectile launch. So 2gm m over 3r less than gm m over r. So it means the conclusion we can say that the projectile will not escape the gravitational field of P. Okay. Okay. Next. I think this is clear. Next. Part B. The surface of P is an equipotential surface E0. The dot circle label E1. This is an equipotential line at a distance 3r half from the center of P. Okay. The potential difference between E1 and E0 is 2.2 times 10 power 6 joule per kg. Question. The radius R of P is 8.5 times 10 power 6 meters. Estimate the magnitude of the gravitational field strength between E1 and E0. Right. Given the potential difference between E1 and E0, the potential difference or delta phi is 2.2 times 10 power 6 joule per kg. Radius, this one, and then distance. Distance from the center to E1 is 3r half. Then delta, I'm going to use in delta r. Okay, delta r is of distance of E1 and E0. Distance of E1 and E0. Okay. Distance of E1 and E0 is 3r over 2 minus r. E1 and E0. And we can determine 3r half minus 2 times r, 2r half, r, 1r over 2. Okay, that is delta r. Next. G is delta phi over the gravitational equal delta phi over delta r. Delta phi is this one, 2.2 times 10 power 6 over delta r is 1, r over 2, or 2.2 times 10 power 6 times 2 over r, or 2.2 times 10 power 6 times 2 over r is this one, 8.5 times 10 power 6. 8.5 times 10 power 6, right? So becomes 4.4 4.4 over 8.5, and the result I have calculated this is 0.4 0.518 Newton per kg or 0.52 Newton per kg. Right. Next, the next question is about this one. E2 is an equipotential line such that the potential difference between E2 and E1 is also 2.2 times 10 power 6 joule per kg. Draw the equipotential line E2 on the diagram. So there is A2 here. This is E0, E1, and I'm gonna add one more circle. Wait. Around here. Okay. E2. Okay. This is E0, E1, and E2. Right. The gravitational potential of wait, the gravitational potential of a distance x from the center of the planet is given by Px equal minus gm over x. This is the gravitational potential at a distance x, if the distance is x. So this is the distance to uh, from P to E2. Okay, so we need to determine first the distance x, right? So this G is the gravitational constant, M is mass of the planet, and x is distance from the center of the planet to E2, right? So it means, oh yeah, I will explain first how we determine the potential difference between potential difference. We are going to determine first the potential difference between E1 and E0. After that, potential difference between E2 and E1. At E0, the potential is at the planet at the planet surface. So distance distance r, and at E0, the velocity at E0, that is minus gm over r. R is distance. G is same as one, gravitational constant. M is the mass of the planet. This is at E0. At E1, the velocity E1 is minus gm over 3r half. Okay, it equal minus gm over minus 2 gm over 3r, because 2 times gm. This at E1, right? And E0 because the distance between P and E0 is r, and the distance between P and E1 is 3R half, right? So the potential difference between E1 and E0 we can determine through delta phi. Delta phi is phi E1 minus phi E0. Phi E1 is this one minus 2 Gm over 3R minus E0 is this one minus Gm over R minus 2 Gm over 3R plus Gm over R or Gm over R minus 2 Gm over 3R. I'm going to factorize Gm over R times 1 minus 2 over 3 or Gm over R times 3 minus 2. 3 minus 2, 1. 3 or Gm over 3R. That is delta alpha or potential difference between E1 and E0. Now we're going to determine the potential difference between E2 and E1. Wait, I have electricity for my laptop. Right. Potential difference between E2 and E1. The potential difference is okay if at E1, so uh, the velocity E1 is minus 2 gm. Which one is now? This one over 3r. Okay, wait. We're connecting to electricity. And we can write the potential at E2 as this one at E2 is phi E2 equal minus Gm over x. Over x, x is distance. It is for the information x is distance the center from the center to E2 because we haven't yet information about the distance of the center to E2. We are going to determine. So it means delta phi, the potential difference between E2 and E1, delta phi equal phi E2 minus phi E1. Phi E2 is this one minus G M over X minus 2 G M over 3R. It equals 2.2 times 10 power 6 joule per kg. And it becomes minus Gm over x plus 2 Gm over 3R equal 2.2 times 10.6. Gm over R we can writing as minus Gm over x equal 2 times 6.6 times 10 power 6 over 3. 2.2 times 10 power 6. I need more space, right? So delta V equal minus, no need this one, because we are going to find x. We're going to find x, it means minus Gm over x plus, sorry, it is plus 2 times 6.6 over 3 is 4.4, 10 power 6. This is plus, actually. Okay. Equal 2.2 times 10 power 6. So minus Gm over x equal 2.2 times 10 power 6 minus 4.4 times 10 power 6. So minus Gm over x equal minus 2.2 minus 2.2 times 10 power 6. That is minus. And then Gm is minus 6.6 times 10 power 6 R over x equal minus 2.2 times 10 power 6. So we can determine x equal minus 6.6 times 10 power 6 R over minus 2.2 times 10 power 6 equal 1. This is equal 3R. So the distance is 3R. Distance of the center to E2 is 3R. It means I'm going to writing the conclusion. It means equipotential equipotential line E2 is at a distance 3R. 3R from the center. From the center of the planet. Okay. So this is a planet with the center P, and this is E0. So the distance from P to E0 is R, and there is, sorry, E2 here, E1 here, E1 here. Center of P to E1 is 3 half R, or 3R half, and there is E2 here. Okay, okay, this is the third circle, E2 here, and the distance between P to E2 is 3R. So on the diagram, E0 is at radius R, okay, and E1 has radius 3R half, and then E2 has radius 3R. A conducting rod of length L is moved with speed v at right angles to a uniform magnetic field of flux density B. The field is directed into the plane of the page. So using Faraday's law or otherwise, the potential difference phi established between the ends of the rod is phi equal phi times B times L. Right. Faraday's law states that the induced electromotive force in any closed circuit is equal to the negative rate of change of the magnetic flux through the circuit. So for a rod moving in a magnetic field, the electromotive force can be calculated by formula, this formula, epsilon equal minus d theta over dt. And uh, the magnetic flux, phi is the magnetic flux. Okay, the magnetic flux phi through the area swept out by the rod is given by this one, phi equal B times A. Wait, I need to fix it. Okay, phi equal B times A, which B is the magnetic flux density, okay, and A is the area. As the rod moves perpendicularly to magnetic field, okay, the area, area A, this area, swept out by the rod, and the equation is A. Okay, if the area swept out by the rods, A is L times V times T. L is length of the road, V is velocity of the road, and T is time. Right. If we substitute this equation A into this equation, okay, V equal B times A, this equation will be like this. V equal B times L V T, like that. To find EMF or electromotive force, we need to rate of change of magnetic flux. So it means, here, it means the theta dt is equal B L V times L times V. If we're gonna find electromotive force, right? Uh, According to Faraday's laws, EMF, that EMF equal this one EMF. Sorry, the yeah, this is the EMF, the epsilon. I mean, epsilon equal the theta over the t. D minus. This is minus because of it's the sign of initial movement. Okay, the initial position, right? So epsilon equal B times L times V based on this formula. Epsilon equal B times L times V. Also, you can write it here negative, 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 right? So this this induction of electromotive of EMF, electromotive force, is the potential difference established between the end of this road, right? So it means potential difference. So the potential difference is phi. So phi equal B times L times phi, according to this formula. If the electromotive force is the potential difference. So based on this result, that we can say that potential difference or voltage equal V, velocity, times B, okay, times L. Yeah. Again, B is the magnetic flux density. L is length of this road. Identify the end of the road that becomes negatively charged. If end of the road becomes then negatively charged. Right. I have provided my explanation about these questions, and you may learn my opinion. The induced current flows in the directions of the second finger, which point upward on the right side of the road. Therefore, positive charge will move. This is actually toward the top of the road. Negative charges will move in the opposite direction to the bottom of the road. The charges move toward the bottom of the road on the left side. The left end of the road becomes negatively charged. Conclusion: the left end of the road becomes negatively charged. Right. Next. Coil is rotating in a region of magnetic field with angular speed 12.56 radian per second at t equals 0. The field is parallel to the surface of the coil. This is the diagram of the coil, right? State the magnetic flux linkage through the coil at t equal 0. All right. Magnetic flux linkage or phi, right? Magnetic flux linkage. Okay. Magnetic flux linkage through a coil is given by the equation that phi equal b times a cosine theta. Right. Again, B is the magnetic flux density, A is area of coil, then this coil, I mean this area, when this coil rotating, it will be implication for uh, the magnetic, the flux magnetic, right? And theta is the angle between magnetic field and normal line to the sheet of coal, right? At t equals zero, when t equals zero, it is given that field is parallel. When t equals zero, that magnetic field will be parallel with the coil area, right? If the magnetic field parallel with the coil area, this means theta will be 90 degrees. So if cosine 90 equal 0, so phi according to this formula, phi equal p times a times 0. So it is 0. It means phi equal 0 if the magnetic flux linkage through the coil at t equal 0, right? T equals 0, it means the initial position. Draw on the axis a graph to show the variations with time of the induced EMF in the loop. The numbers are required on the vertical axis, right? So now I show you that at the initial position when t equals 0, phi equal 0, right? Now, I'm going to using the formula of phi on the initial condition that minus BA cosine omega times t. Okay. Now, omega is this one. Then the number omega, uh, this one. The angular, omega is the angular speed, 12.56 radian per second. So I can write this equation or this formula becomes minus BA cosine 12.56 T, like that. Right. Now, if on this graph, if T equal, this time if T equal 0, and if you substitute into this formula, you can find that minus BA cosine 0. Cosine 0 is 1. It means minus BA. And if T equals 0.25, if T equal 0.25, phi equal minus BA cosine 12.56, 0.25. the result is the result is um, minus. Sorry, the result I have calculated 12 times 1, 3.14. It means cosine p, and the result phi is 1. Cosine 180 is 1, so it's minus 1, sorry, minus 1, so it becomes positive BA. Okay, and how about if t equals 0.5? This one, if 0.5, t equal minus b a cosine 12.56 times 0.5, and the result is minus, okay, minus b a, right? So if we sketch becomes like this. I would like to determine, for example, 1, 2, 3, 4, 5 is if BA here, and then 1, 2, 3, 4, 5, 7, 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4, 5, 6, 7. Here, minus BA. Okay, so when t equal 0, the coordinate point here. When t equal 0.25 here, coordinate point. When t equal 0.5 here, so we can create. Wait, I will using the different color. Okay, and then like this. Right. That is the period already done from this one to this the period half period. It means will be it will be repeat periodically the trigonometry graph. So it becomes here. Okay, like that, and here. Okay, like that. A capacitor is connected to a cell. The switch S is closed and the capacitor becomes fully charged. This is the circuit. A dielectric is then inserted in between the plates of the capacitor. Suggest what, if anything, will happen to the charge on one plate of the capacitor. The charge on one plate of the capacitor is given by the formula Q equal, wait, Q equal C times V. What's that? Wait. Q is charge, and then C is capacitance of the capacitor, while V is voltage or potential difference. So if in the circuit, voltage or potential difference, it's always same. It will be same, right? The difference only the increase or decrease the capacitance and charge. So if voltage or potential difference always same, it means if capacitance increase, if C increase, if C increase, also Q will be increased. Okay, automatically. And the implications, if capacitance of capacitor increase, and if the capacitance of capacitor increase, the charge will be increased. Why the capacitance capacitor increase? Because the electricity flows, okay, in this circuit. Yeah. Why it flows? Because the switch is closed. This diagram show us that the switch is open, and when it closed, it means the electricity will be flows and then becomes fully charged. If it's fully charged, it means the capacitance capacitor will be increased, and the implications as well, charge will be increased. Number 10, in the Bohr model for the hydrogen atom orbital angular momentum is quantized. Okay, this formula MVR equal n times h over 2 pi outline the effect this has on the electron energy. All right. In the Bohr model, the angular momentum of the electron is quantized. I would like to write in here the angular momentum the angular momentum of electron one already that is the angular momentum of the electron is quantized according to this information. Okay, and this statement given by the formula is this one mvr equal n times h over 2 pi. This is the formula. It means the electrons can only have specific values of angular momentum. Okay, because the angular momentum is quantized. The allowed orbits and their corresponding radii is also quantized. Right? Again, if uh, if the allowed orbits and their corresponding radii are quantized, it means the angular momentum is quantized. The angular momentum, if angular momentum quantized, so it means the implication that the ready also quantized. Ready also quantized. Its allowed orbit corresponds to specific energy level, okay, through the statement, which is given by the formula of this one, the formula En equal minus 13.6 electron volt over N squared. Now pay attention that the sign is this one, minus, right? So the energy of the electron in the Bohr, in the Bohr model, okay, in the Bohr model, is indeed discrete and quantized. Okay, again, the energy of the electrons in the Bohr model is indeed discrete and discrete and quantized. Okay. I just reviewed this lesson. I have explained this on my lesson in the classroom. For the hydrogen atom, the radius of the electron in the n equal 2 state is 4 times larger than the orbit radius in the n equal 1 state. Determine the ratio V2 over V1. Okay, V2 when n equal 2 and V1 when n equal 1. Of the electron speed in the n equal 2 state to the speed in the n equal 1. All right. The speed of the electron in a given orbit in the Bohr atomic model is inversely proportional to the principal quantum number, the quantum number n. This one, n. Okay, so n equal 2, n equal 1. So if I will writing the relations is Pn equal k over n, which k is constant number, right? K is constant. We can state the speed when n equal 1, when n equal 1, the velocity will be v1 equal k over 1, and it is k, this is k. And when n equal 2, it means the velocity, the v2 equal k over 2 or half k. This way now, we can uh, we can compare that v2 according to uh, this statement v2 over v1. Okay, the ratio we are going to find. So v2 is this one, k half over k, or k half times 1 over k. It is 1 over 2. So v2 over v1, the ratio is 1 over 2 or half. Compare and contrast the Bohr prediction for the radius of an electron orbit in hydrogen to that of the descriptions of the electrons in terms of wave functions. In the classroom, I have explained this, and we have I have many sentences for explain these questions, but I have provided my explanation here. Okay, and this one, my explanation in this video. Bohr's model treats the electron as a particle in a classical circular orbit with a specific quantized radius for its energy level. The quantum mechanical model based on wave functions does not have definite orbits. Instead, the electron's position is described probabilistically. Okay, and next, the Bohr model gives us a definite prediction for the radius of the electron's orbit based on quantized angular momentum. And the quantum mechanical model provides a probabilistic descriptions of the electron's position with a most probable radius but not definite orbit. The quantum mechanical model explains the Bohr radius as the average distance of the electron from the nucleus with a spread of possible positions around the value. In the classroom, I have show you my opinion about these questions, and this is not enough if I will typing here. So the comparison and the contrast between the Bohr predictions and also the uh, wave functions. Okay, next. Determine using the uncertainty principle, the minimum kinetic energy of a neutron inside a nucleus of radius 3 times 10 power minus 15 meters. Right. We're going to determine using the uncertainty principle. We are going to use Heisenberg uncertainty principle. According to Heisenberg uncertainty principle, to determine the minimum kinetic energy of a neutron inside a nucleus, we can use this inequality that delta x times delta p greater than or equal h half, which delta x is the uncertainty in position, delta p is the uncertainty in momentum, while h is reduced Planck constant. Reduced Planck constant is this one, h equal 1.054 times 10 power minus 34 joule-second. For a neutron inside a nucleus, we can take the uncertainty in position delta x to be approximately the radius of the nucleus, that delta x, okay, that delta x equal 3 times 10 power minus 15 meters based on this statement, this information. Okay. Through the uncertainty principle, this one, we uh, we gain with delta p. Delta p greater than or equal h over 2 times delta x. So delta p greater than or equal, we're going to substitute this number 1.054 times 10 power minus 34 over this is delta x 2 times 3, 10 power minus 15. And if we calculate, this is delta p greater than or equal if to calculate, it is 1.76 times 10 power minus 20 kilogram meter per second. The minimum kinetic energy, okay, the minimum kinetic energy of neutron related to momentum, neutron related to momentum, to P, okay, momentum, we can gain through this formula that kinetic energy equal delta P squared over 2m, which m, I'm going to write in here, m equal mass of a neutron 1.675, 10 power minus 27 kg. This is mass of neutron. So delta P is 1.76 times 10 power minus 20 squared. 2 times 1, 1.675 times 10 power minus 27. And the result is 9.24 times 10 power minus 14 joule. As we are going to convert to electron volt. So convert to electron volt, I'm going to inform that 1 joule is 6.242 times 10 power 18 electron volt. So kinetic energy equal 9.24 times 10 power minus 14 is 1 joule. Is this number, it means multiply 6.242 times 10 power 18. And the result is 577 kilo electron volt. And I like to simplify or convert into mega electron volt. It means divided by 1000. 1 over 1000 mega electron volt, and it is 0.577 mega electron volt, and it is 0.58 mega electron volt.